Thank you very much, Kai. It's really nice to be here. The last time I spoke, I got an equally beautiful poster. That was maybe 10 years ago, talking about making skyrmions in Bose condensates. This is a very different kind of a topic, and I'll tell you a little bit about how I actually got involved with it. And it's really a technology demonstration and development project connected to what you can do with cold atoms in space. So that's the topic that I want to tell you about today. So I will claim that, and even more importantly, NASA now claims that this is the coldest spot in space. And you might think that that's somewhere deep out in outer space, but arguably it's not. It's on this funny thing here, the International Space Station, and it's taking place inside of this little module here that is this cold atom laboratory. So I want to convince you that at least there's a good reason to call this the coldest spot in space. Why do you want to do physics in space? Well, there are many different kinds of reasons you might, but particularly if you're a cold atom person, there are many advantages. In microgravity, you don't necessarily need a trapping potential. And for many of the things you want to do with cold atoms, the trapping potential is an enormous perturbation on the system. And if you can eliminate that, you can do things that you can't do on an earthbound system in any sensible way. You can also have very small gravity gradients, and this means that you can have very homogeneous samples. And I'll tell you a little bit about some of the work in superfluid helium that has been a demonstration of how important that is. Space is arguably a very low vibration environment with a high degree of isolation. But I think physics-wise, the most important thing is you can access different space-time coordinates. And that sounds like a fancy thing to say. What it really means is, for example, gravitational redshifts. You measure the performance of a clock on Earth, you measure the performance of a clock in space, and you can make tests of general relativity by accessing a place where the gravitational potentials are very different. For the point of view of cold atoms, it also means, and I'll show you what I mean by this, you can get very long observation times. But probably the most persuasive thing from NASA's point of view is this ability to do sort of pathfinder experiments on quantum technologies, and I'll tell you what I mean by that in space. My own involvement with this program actually began frighteningly long ago. It began in 1998 when I was recruited to join a group of people advising NASA on doing fundamental physics experiments in space using the space shuttle with an eye towards the emergence of the completion of the space station. This came out of a low-temperature physics community that was finding funding a challenge, but also was interested in the science you can achieve when you have samples of, say, superfluid helium in which there is a no density gradient that's caused by gravity. They realized, I think quite wisely, that getting cold atom people and some of the community involved in that program would make it stronger and better. So I agreed to do that. At that time, it was completely advisory, but just to give you a sense of what I mean by what can be done, this is a space shuttle experiment that was done by a guy named John Lipa, and it's measuring the superfluid phase transition in liquid helium. And what was remarkable about this experiment is that by getting into a gravity-free environment in the space station, where the gradients in density are almost absent in the superfluid, at a 1 degree temperature, they were able to nail down the width of that transition to a nanokelvin. And we're very familiar with nanokelvins now when we do cold atom physics, but 1 nanokelvin out of a kelvin is a hugely important accuracy and allows you to look into things like normalization group calculations of how that phase transition should take place. NASA was building up quite a big program. A number of Nobel laureates in the United States were funded, atomic clock experiments, a whole variety of things. Unfortunately, politics took over, as it often does. The space station cost overruns were plaguing NASA. The shuttle blew up, and that was a pretty dramatic thing to shut down the program. And the administration in the White House at the time said, we're going to shut down all of this space station business and we'll go to Mars. That's a great, in my own colloquial, that's called kicking the can down the road. It doesn't solve the problem, but it's a distraction from the cost overruns of the space station. Unfortunately, when you do politics, you also find that you get a bunch of very outspoken scientists who aren't shy about expressing their dismay with NASA's choices. So the whole program was canceled. And when it was canceled, people began to protest and write letters to Washington. But there were other very creative scientists in the community, most notably in Germany, who were doing microgravity experiments, although very brief ones. This is a drop tower. It's about 120 meters tall in Bremen. If you're an experimental person, you should be impressed. 120-meter tall tower, and you pump it down to about 10 pascals. And then you drop a payload that has your experiment in it like that. It's about this big around. It's about my height. And it drops for 5 seconds, and it stops at the bottom. And there's a very, very high-tech technique of stopping it. You know those packing peanuts that you ship things in? There's a bunch of those in the bottom. Remarkable, but they made this thing, and they would drop it, and it would still work at the end of the drop, and they'd do it over and over again. There was also a series of experiments a bit later using a sounding rocket. So this is a rocket that launches and in parabolic flight now has a more extended period of essentially gravity-free time that you can do BEC experiments. And the group demonstrated that they could not only do a Bose condensate, but they could make an atom interferometer work. When the politicians in Washington got enough letters and enough protests from Nobel laureates about this horrendous decision to shut down the program, Congress then did something unusual in the United States. It required NASA to get the National Academy of Sciences to write a report with a 10-year plan. And this is how things like planetary science and astronomy are done in the US, because so much money is involved in the investments. And I was part of writing that report. When NASA got that report, they very quickly moved, and they decided what they would do is to build something, which was, I think, kind of a remarkable idea. I'm not sure positive or negative, but was to build a facility and then see if scientists would use it. And that facility is called the Cold Atom Laboratory. And the system hadn't even been built, but they were saying, here's what we're going to offer you. We're going to offer you Bose condensates produced by laser and evaporative cooling. We're going to give you 2 different species, rubidium, potassium, fermionic and bosonic isotopes. We're going to give you lots of imaging capabilities, and we'll do RF and various things to allow you to do quantum state preparation. And thanks to several of us that lobbied hard, we're also to build in the capability to do atom interferometry. So that's the coolest facility, figuratively speaking, on the space station. And NASA went ahead and started to solicit proposals from people when there wasn't even a facility. Now, for those of you that work in experimental atomic physics, you know one of the difficulties of this idea is this is my laboratory circa 10 years ago. So you can imagine how much more stuff is on that table. It's a room full of stuff, and you think, how on earth is that going to go on the space station? No pun intended. So the challenge is, how do you make that work? Well, the people at JPL decided what they would do is they would start by partnering with Cold Quanta to build one of these double vacuum system cells for producing a Bose condensate. There was a little atom chip at one end of the cell, and then they integrated that into a system that could then fit aboard the space station. And the module for the primary part of that system, the vacuum, shielding, optical access, all those kinds of things are in this object here, which is about that big. Now, there's the way that the layout of the system works is that there's imaging beams, there's Mach beams for the cooling and the trapping. And one of the things you also learn about when you work in the environment of space is that things like convection don't work. There's no buoyancy. So if you get something hot, it doesn't cool off very easily. So you have to really work hard to make sure you can control the temperature and dissipate all the heat associated with doing various kinds of things. And what you see is here is this is the science cell buried in here. There's the bottom part, the condensate forms up here. And all this stuff here is just simply to carry heat away. This I like particularly because I claimed at the beginning that space is a very low vibration environment. The place they chose to install this thing on the space station is right next to an exercise bicycle. So one of the things you learn is you have to work with the fact that there are astronauts aboard the space station, and they are your partners if you have to do certain kinds of operations. So the first thing to do is to look at what the formation of a Bose condensate looks like in a terrestrial experiment. This was in that actual apparatus, but on Earth. And evaporative cooling is taking place from left to the right here. The sample is then released. You do this absorption imaging, and it's the formation of this small peak here that you recognize as the formation of the Bose condensate there. Now, you take that and you bring it to space. It looks more or less the same at a glance. This is the first Bose condensate in what's now the traditional way, since that cover of Science magazine had the first condensate from the group in Colorado. And there, lo and behold, is this nice little sharp peak that is recognizable as the signature of a Bose condensate at about 90 nanokelvin. When you start to look at things in detail, you discover that already it doesn't work the way it does on Earth. When you do evaporative cooling, you have a magnetic bowl. You put the atoms in it, and you induce spin flips that eject the hottest atoms out of the bowl, and then collisional cooling takes the residual temperature of the remaining sample to lower and lower temperatures. On Earth, when that happens, those atoms are either ejected or they fall out under the force of gravity. They don't do that in space. So while this is what it looks like as you form the Bose condensate on the ground, when you do it in orbit, all those atoms you kicked out sort of float around nearby. And that's part of what you want to have happen, because that means that the atoms stay untrapped in the region for long periods of time. What you're seeing here is a demonstration of taking that sample and applying a magnetic field gradient. So you're taking advantage of the Stern-Gerlach effect. This is the mixture cloud here. You do a Stern-Gerlach, the BEC is in a F equals 2, M sub F equals 2 state, and is pushed away by the magnetic field. And that remaining cloud of the evaporated atoms that's in the 2-0 state essentially sits still in space. And you can do that with a field gradient in two different directions and find that there's even a small residual amount of states in the other M sub F states. So already evaporative cooling is working differently. Now, what about the observation time? For this particular system, for its vacuum, here's the condensate, here's some of that residual cloud from the evaporation, and then you observe it and see how long you can have it just hover in space. It turns out that when you turn off the magnetic fields in this system, you give the atoms a little bit of a kick, which is unfortunate, but it's a practicality of how that chip was designed. But something like almost a second later, the atoms are still hovering around. And these are just basically measures of how the anisotropic expansion happens due to the fact that the trap is asymmetric. So, Cold Atom Lab, it's producing condensates, it's working and ready to go, and NASA seeks proposals. Up to this point, as Kai had mentioned, my role in this was really with a group of external scientists sort of advising and giving recommendations on what to do. We were a little bit worried that NASA had built this rather expensive apparatus, $60 million, and that there wouldn't be a lot of scientists who would think that it was worth their time to try to do work with it. So we formed a group that is called the Consortium for Ultracold Atoms in Space, and it has a variety of institutions involved, most notably my own institution, of course, but also recognizing that work in the drop tower and the sounding rockets taking place in Germany. I brought in for that consortium some partnerships from Germany. And NASA was quite happy with that. All they said is we can't send them money. But the money that's involved is using that apparatus. It's flying around up in space. So I want to talk about a few things today that we've been working on. Quantum gas physics, in particular mixtures and shell geometries. I want to talk a little bit about precision measurements. We're early into the phases of doing interferometry, and this is really an application down the line in terms of geodesy. So the sub-team from that consortium of people that's been really spending a lot of time focusing on what to do, and what we've been doing with the CAL device in the space station is my group, Holger Müller at Berkeley, Ernst Lasel and Nasser Galul at the Leibniz University in Hanover, and Wolfgang Schleich and Matthias Meister at Ulm. And because most of us recognize that an engine of much of this work are graduate students, there are a lot of people listed here. Well, certainly not Wolfgang and certainly not Ernst, but the graduate students who really do a lot of the calculations and modeling that guide the work that we do together. So this is the first BEC that the consortium made. I made it. I got the fun to travel to JPL. I got to sit at one of those, workstations in the control center in JPL, and I got to hit the button on the keyboard and bang, a BEC forms. Now, mind you, this is 350 to 400 kilometers up and traveling at almost 30,000 kilometers an hour. So it's kind of a strange thing. The possibility of just doing that to me was, I have to confess, at certain times on this project, I feel like I'm 6 years old again. I certainly felt 6 years old then. It was just very exciting. Now, where does work begin? Work begins, you've got this atom chip that Cold Quanta produced, and the BEC is formed right next to that atom chip. And that's a wonderful way of producing the initial cold atom sample and the Bose condensate, but it's not in a situation that's as easy to do high-quality experiments. There's several aspects of that, one of which is that if you leave the BEC near the chip and it hovers around for a second or so, it's going to expand and it's going to hit the chip, and that's going to be the experiment. So you need to get it away from the chip. You also need to get it away where you can do high-quality imaging of it. And the trick is, how do you move that condensate from here to another place in an environment where every bit of energy you put into that can ruin the experiment or can sort of effectively destroy the advantage of having been in space in the first place. So you might think, well, that's pretty easy. You'll just take a trap that's near the surface of the chip. You'll transfer it into a trap that move that trap away from the chip. Maybe you want the trap to be a softer trap and more relaxed, which is what we wanted. And we decided that we wanted to move it about 1 millimeter out here. And you might think, well, that should be easy. And the answer is yes and no. And I'll give you some graphical sense of what I'm talking about. But the analogy that I want you to have in mind is, imagine I gave you a bowl full of water and I said, start here and run to the back of the room and don't spill any. And I want you to stop at the back of the room and I want the water to be dead still. Here's a way of visualizing what I'm talking about. This is apparently something astronauts do for their spare time. They play with water in space. So the surface tension keeps the water as a blob. These little paddles have a hydrophobic surface coating. But you can see that trying to move the water around creates all kinds of dynamical excitations. Those represent heat. They represent energy. They represent what you don't want to have happen to your Bose condensate. Now you might think, well, the easy thing to do then is adiabatically, so I'll just walk really slowly with my bowl of water. The problem is that it takes, to go for that 1 millimeter distance, will take you about 100 to 150 milliseconds. That's just too long. In that time, you'll lose a lot of the sample, and that will effectively degrade anything you wanted to have in the first place. Also, we're looking at very, very soft traps, so that when we then release the condensate in the position where we want it to be, it has a minimum kick to it. And adiabatic is just not good enough. So we turn to an approach which is called a shortcut to adiabaticity. And it's really conceptually a fairly straightforward thing. It's more of a calculational issue, but the trick is how to set up that calculation to be efficient and effective. You set a set of boundary conditions to the equations of motion. You insist that the sample starts nearly at rest at one position and ends up nearly at rest at the final position. And then you take some trajectory for the frequency and position of the trap and its centroid, and you model it and iterate until you start to meet these boundary conditions. Part of the trick for us to make that work well was to take what could be a very complicated set of magnetic fields produced by this chip and reduce the number of free parameters so that you can actually effectively come up with a shortcut to adiabaticity that's easy to implement with an apparatus that wasn't necessarily designed for it. So when you do that, you start with the initial trap design, you do a transport, you get into the final trap, and you look at things like what are the dynamics of the condensate when you start here. It can slosh, it can breathe, what it's doing. You look at the transport through this shortcut to adiabaticity, and then you look at the behavior of the condensate in the final trap state here. Now that was done with a model. That model was not just a simple finite element calculation of the current distributions on all these little wires on the chip. Instead, it was that model taken and experiments were done to iterate that to find out exactly what the true current magnetic field distribution is like from those. And then you implement the shortcut to adiabaticity. So we spend a good amount of time calibrating the chip model for this structure here and the field coils around it, which were not possible to do on Earth because some of these traps are so shallow that they would not support the atoms against gravity. So what that amounts to is you end up looking at this optimal transport. You study what's going on in the initial trap when you start the transport process. You look at things like the time of flight oscillations of the condensate in that trap. You transport it, and then you look as a function of time at the end, final trap, how its position is oscillating and how it's breathing. And you build those together. This is a sketch of what the shortcut to adiabaticity predictions were, and you fit that to figure out how you can place the atoms at the lowest possible ending velocity at a position of your choice. This is the kind of thing that the data we produced and looked at. This is a subset of many, many runs of data, and keeping in mind that the ability to get data down from the space station in terms of images is a very slow process. These two traps here, this sort of red or tan color and the blue color, are looking at the in-trap amplitude. So here is a very large amplitude. This trap here, represented by this trap here, which is the velocity, is a very soft trap. And the fact that it's very soft means that the breathing excursions are much longer for a given amount of excitation. And the tighter trap is this blue one. And this trap here has different properties in terms of how it kicks the atoms when you release them. So you look at a lot of data like this and you spend time optimizing what you're doing with the sample. One of the things that startled me personally, just because reproducibility is hard enough in a lab that's in the basement or in a building on the Earth. Here is data that was taken in a set of those experiments in October. There was a hiatus. The system was down for technical reasons that I'll mention in a little while. Put it back together in May, and sure enough, the data is falling within the same region over months and months of time. So how do we do in all of that? We transported it about 1 millimeter at a velocity of about 6 millimeters per second using the chips as well as some external coils around the sample here. We moved it a distance that's approximately 1,000 times the size of the cloud. So that, if you think of that little cloud of atoms as your quantum system, 1,000 times its physical size. But what we were very pleased with is that we were able to deposit it at the final position with a final velocity of something like 50 microns per second, and to position it within something like 1/10 of a micron. And that you could not do in a terrestrial experiment because of all the perturbations of gravity. And in fact, that positioning accuracy is comparable to the best thing you could do in a terrestrial experiment using ions. Now, another one of these movies, but this one captures something. You might recognize this guy. I'm forgetting his name at the moment. There were a series of astronauts that have been at the space station. Two have been particularly interesting to us. One of them is a pair of twins, and there was a brother that stayed on Earth this chap spent like a year up on the space station, and the two of them agreed they would be the terrestrial part of the experiment and the flight part of the experiment. But I'm not mentioning it for that reason. I'm mentioning it because he's also playing with water, which seems to be, again, but look at the dynamics of that and think about this being your condensate. At a couple points, he hits that blob of water just right, and it was quite excited, but when he hits it just right, it's excited, a lot less excited. It's not gyrating as much. So this shows that you can, by the way you effectively hit this classical fluid, you can affect the excitations of the fluid itself. So in the language of cold atoms, that's what's referred to as delta kick cooling. It amounts to taking the final trap and flashing it off and on in a very controlled and deliberate way, such that you catch it in its excitation motion and cause the excitation to be damped down. This is referred to as delta kick cooling, and this is one of these graphical pictures where free evolution without the delta kick cooling gets a much larger peak, and in this case, in one dimension study, the expansion velocity is greatly reduced. If we look at that ballistic expansion, this is the case of atoms. If you don't do this controlled delta kick cooling, this lensing in phase space, and you can see just right away, this is the diameter of the blob of atoms as the BC as it expands. It's clearly expanding at a much lower rate if you do lensing just right. And I hope we can convince you that we have. The first round of experiments in doing that, we started out with something like 20 nanokelvin atoms. That's not a typical starting point for a Bose condensate. And we got it to the point where within the error bars, it was a fraction of a picokelvin. Well, we looked at the data very carefully. We looked at how to model it in terms of things like the details of the pulse shapes that are used to do this delta cooling process. This, for example, is one of the delta cooling experiments that we're most proud of. We achieved something around 50 picokelvin final temperature, and that's about as cold as anybody has ever produced atoms in a terrestrial experiment. In fact, that's in Mark Kasovich's experiments at Stanford, where he's doing interferometry in a tower that's something like 30 feet tall, or 10 meters tall. And we were able to do pretty darn well in terms of the delta kick cooling in an orbiting lab way up in space. So what we've learned how to do is we've learned how to shuttle this neutral atom cloud around in space. We've transported over reasonable distances using traps and final states that are sort of as much softer than you could ever use in a terrestrial experiment. We've got very, very low excitation levels, 0.4 microns. So think of human hair as 100 microns. That's a lot smaller. And we've got expansion rates that are now in the picokelvin. So all this you could view as effectively quantum state preparation of the sample on orbit. Oops. So what's next? This is a multi-user facility. What we want to do now is look at atom interferometry. Now, as it turned out, when the initial Cal Science device was launched, there were problems that were had with the cold quanta cell. There's a process they don't want to talk much about in which the atom chip is fused onto the vacuum cell at the top. They call it anodic bonding. But there were several failures, and one of the things you can't afford to do is to build this expensive thing and have it fail on launch. At the time, it was thought that some of the failure for the bonding, the vacuum failure, was due to the introduction of some elements for doing atom interferometry. I'll mention those in a minute. And so the initial system that was launched was incapable of doing interferometry. Several of us spent quite a lot of time persuading NASA that atom interferometry, a quantum sensor, was a truly important thing to do for both fundamental physics and quantum technology, and that it was worthy of the cost to then launch a second system that was atom interferometric capable. And I want to tell you a little bit about how. Now, the underlying motivation for doing this was quantum sensing, like gyroscopy, rotation, acceleration, but also doing universal free fall. This is the weak equivalence principle concept, namely, do things of identical, different compositions fall at the same rate under gravity. In this case, the different composition are atoms, rubidium and potassium. So none of the shape effects, for example, that you might be worried about come into play. The question is, can we do a cutting-edge equivalence principle test on orbit? So atom interferometers are based on the same concept as light interferometers. The most familiar for things like quantum sensing or classical sensing is the Sagnac interferometer. It's a Mach-Zehnder interferometer, and it's kind of a circular geometry. And probably you've flown in an airplane that's used one of these gyroscopes that's made of an optical fiber as part of its inertial navigation system. Of course, you can do that with atoms as well. Atoms, as this guy Louis de Broglie and later this guy Steve Chu demonstrated in the laboratory, make very nice particles for interferometry. And unlike light, they have the virtue that they do couple to gravity. They do couple to other things in the environment, like magnetic fields and so forth. So the question is, can we do high-grade atom interferometer experiments on the space station? The basic idea is pretty straightforward. You propagate in time in this direction. You have an atom, for example, here. You hit it with a pi/2 pulse that places it in a superposition of states between two of its states. One of them acquires a certain amount of a momentum kick from the photon. You hit it with another pulse a certain time later, a pi pulse. You again branch in two different directions, and then later another pi/2 pulse, and you recombine. And depending on the path length difference, or effectively the phase difference around that loop, you can look at the output ports here, and depending on the phase difference, the amplitude, probability amplitude for the atoms to be here or here oscillates in time. The trick is now we want to do that aboard the space station. So we want that process, and we want to modify the cold quanta cell design to do that. And the way that was done was to put a window in the chip. So there's a small aperture that the light can go through. There's a mirror at the other end of the cell, and you send a light beam in and bounce it off that mirror. It forms a standing wave, and that standing wave is the effective diffraction grating off of which the atoms scatter to form the beam splitters and mirrors that form that interferometer. And then you want to take that whole thing and put it up on the space station. So as I said, the motivation that we used in the proposal to get them to spend the money on doing that was at a fundamental level to look at weak equivalence principle. Interferometers are also wonderful ways to look at fundamental constants. I won't try to explain all of the nuances here, the time dependence of fundamental constants and things of that sort that have been motivating lots of atom interferometer work in many different locations. But I think what's really, truly important in the case for interferometry in space is inertial navigation, gravitometry, planetary exploration, and so forth. These are just wonderful sensors, and if you can get them in space, you can do things that you cannot do in a terrestrial environment. So the design was basically, as I indicated, a different kind of a chip here with a hole in it, a mirror at the bottom, and some extra laser equipment. The kind of things we are working on are differential gravity measurements using rubidium, potassium, or rubidium, potassium-41, fermionic or bosonic, trying to do gravitometry and gradiometry of those gravitational measurements, but also to demonstrate rotational and vibrational sensing of the ISS. A pretty mundane thing, but if we can demonstrate the ability, for example, when they boost the ISS, every so often they give it a push upwards, we can measure the accelerations and the torsion that happen in the space station. We're demonstrating that quantum sensors can actually do useful things aboard the space station. So that was launched aboard a SpaceX Falcon, December of 2019. The modified system is shown here. And before launch, it was demonstrated that most of the aspects of the interferometer would work. And again, I want to emphasize that we can't test everything on a terrestrial experiment before launching it, because we're going to do experiments with the conditions that we can't produce on Earth. Of course, this is where I turn 6 years old again. I got invited to go to the launch. Back when the space shuttle I went to a space shuttle launch, and there's a little story that goes with it. I would have thought this is at Kennedy Space Flight Center in Florida in the United States. When I first saw the shuttle launched, I was really impressed because when the shuttle launched, you can feel your body shake. You're not that close, but you're close enough. And all the cars in the parking lots, the sort of car alarms go off. You're just parking lots, so, this sort of sound, Here it is, 12, 15 years later, same story. They launched SpaceX, all the parking lot cars are going off. But the most fun part, of course, for me was there I am, right next to a SpaceX rocket. So you get to go see the launch, but the launch is quite a distance away. Here it's being launched in 2019. And this person here is Christina Koch. You probably don't recognize, she was the woman playing with the guy with the blob of water back and forwards. She holds the record as being the female who's been on orbit for the longest period of time ever. And it turns out that, like people, not all astronauts are created equal. Each astronaut brings different sets of skills to their role as an astronaut on the space station. She was the person who was both interested in, because of her own PhD background in physics, in fact, in cryogenics, of helping us out. And she had the interest and dexterity to do things like recouple optical fibers and things. She did the reinstallation of the interferometric capable module in this, and 4 days later came back to Earth. Oops. So you've got this apparatus up there, and you start to do the testing to demonstrate that it works. You demonstrate that you could do a beam splitter. So that's that first step here. Here, the BEC is now beam split into two components. One sits still and the other goes wandering off with 2 h bar k of momentum. I want to tell you about a couple of different kinds of interferometers that we worked with. A 2-pulse Ramsey shear interferometer, and a 3-pulse Mach-Zehnder, and a 4-pulse differential. The Mach-Zehnder is the one that's most typical of, say, a gyroscope like the Sagnac interferometer, and the 4-pulse is effectively 2 interferometers in series that allow you to do gradient measurements. So a shear interferometer, this is one that most people aren't as familiar with. It's a very simple kind of interferometer because it uses 2 Bragg pulses, pi over 2. So you're again propagating in time. The first pulse leaves some of the sample at rest and some of the sample with 2 h bar k of kick. And then you do that again, and you again form the 2 different branching. You end up with a cloud that's here at 0 h bar k and 2 h bar k. But what this sort of schematic diagram misses is the reality that in that evolution, the cloud still has a finite temperature and is expanding. So this is the cloud's size as it propagates down through this interferometer. What that does do is it works in your favor. That means that as you look at the clouds as they begin to overlap downstream, you see fringes. And those fringes are a measure of what's going on in terms of their wavelength in the evolution, the temperature characteristics of the Bose condensate that you're using for your experiments. So that's the schematic. If we look at the fringe spacing, so here are fringes after a certain amount of propagation time, a bit longer propagation time, you can see 3 fringes here. By the way, if you are at all familiar with interferometry, the fact that these fringes are so widely spaced shows you just how cold that sample really is. The de Broglie wavelength is very, very long. This is the fringe spacing as a function of the evolution time. This curve here represents exactly what you would expect as these clouds expand outwards. And just for the sake of the understanding of the physics of this curve, at very short times, the cloud is dense enough that mean field interactions between the atoms affect the way the cloud expands. As it expands further and further, it's all kinetics. So we then worked on a Mach-Zehnder, accelerometer, and magnetometer. The way you might imagine this is if you include acceleration into a picture like this one, That represents, as the clouds move, a curvature. That curvature is the acceleration that could be produced by a number of things. In our case, the most significant contribution to that curvature, to the acceleration of the atoms, is the residual field gradients inside of the chamber. These are field gradients that are not imposed from the external world. They're residual gradients from the magnetic field coils, from the mu metal that's not shielding things perfectly. But we decided that was a great thing to use to sort of calibrate and demonstrate doing magnetometry and gradiometry. So you follow the world line of each of these two components of the cloud, and what you end up doing is measuring in an absorption image and extracting populations for each of the two components that come out of the interferometer. You measure their separations, and you measure the number in each component of the cloud as a function of whatever is causing the phase difference between these two paths, in our case, the magnetic field. The interferometer works. So again, that's the schematic of it. This is what the typical output images look like that are then sent back for analysis. There's a little tiny bit here of residual of one of the components that wasn't in this simplified version of what the trajectories look like. And as you look at the phase difference between the two paths, you see just what you would expect between the two output ports, a sinusoidal oscillation backwards and forwards. So interferometry works. We do a fairly, you do the experiment over and over and over again to build up statistics. You do a more careful analysis. You have to worry about things like, what is if you know the language of Bose condensates, what is the distribution function for those clouds, the Thomas Fermi radius, the residual thermal radius, and you put all those ingredients in to see how far you can push the analysis. Now you can do that, as I said, in a 4-pulse configuration, where you have a pi over 2, then a pi over 2, pi over 2. And if you follow the primary trajectories here, you can see what this effectively does is it creates two Mach center interferometers that are spaced by some distance, and the phase difference between the two represents the gradient now that's between, say, the two magnetic fields, or the magnetic field that's producing that phase shift in each one of the individuals. And the data you get back looks like this. And each of these clouds you attribute to one of the output ports, 0 and 2 h bar k from this interferometer, and 0 and 2 from that interferometer. When you look at how to represent that data, if you basically look at one of the interferometers output port balance versus the other, you get, because of characteristics of the imbalance in the interferometer, an elliptical shape. If it was perfectly ideal, if the two populations were perfect pi over 2, pi pulses and things, this would be a circle. The slight asymmetries give you an ellipse. And if you look at the angle of that ellipse, it tells you about the gradient that's present between those two interferometers. So looking at different interferometer times, these are relatively short compared to what you would aspire to use, say a millisecond, 2, 3 milliseconds. You can look at the shape of this and the angle of that ellipse, and depending on the time delay, you can see that the ellipse is rotating. That rotation is due to the gradient in the field between the two Mach centers. To make sure that you know what you're doing, you do a state preparation experiment in which you take the BEC that you've produced. The starting condensate is in a F equals 2, M sub F equals 2 state. That's a Zeeman sublevel that's magnetically sensitive. That's great if you're trying to detect magnetic fields. But you also then do an adiabatic rapid passage, and you transfer all the population to the 0 Zeeman sublevel, which is now magnetically insensitive. You do the same kind of analysis, no more ellipse or circle, and no rotation as a function of time. So we're able to demonstrate that this is truly due to the magnetic fields and not some other source of a phase difference between those two Mach centers. The analysis of the phase scan gave us a pretty crude gradient measure in this case. It's something like 190 milligauss per centimeter with an accuracy that's something like 0.5%. And you can also look at the overall center of mass motion of the cloud due to that curvature in the magnetic field and do a cross-check between the two. And sure enough, the slope of the center of mass motion tells you something about the field gradient with not nearly the kind of precision that an atom interferometer offers to you. So we've got different geometries of interferometry. We're looking at how we can push it further and further in terms of that time. Things like how uniform the light pulses are, not just in time, but in space, become truly important. That little window I mentioned in the chip, bad stuff. It's not a nice high-quality window that you'd have in a vacuum system with air coatings. It's a little piece of silicon wafer with a window glued to it. And that causes all kinds of ripples and distortions. And we're working with atoms that are so cold that the non-uniformity in the laser beam profile causes small distortions in how the atoms themselves move. We're trying to conquer that one. But the next things we want to do are start doing inertial sensing. And it's hard to believe, but they've agreed to start coordinating when they give that space station the little kick with us. So when they're kicking it, we can measure the acceleration due to the kicks. We then started to work on the fact that this system also does rubidium and potassium. I won't go into details of how it all works, but we began to do shortcut to adiabaticity protocols so we could move now rubidium and potassium both together to where we want them with minimal residual accelerations and excitations. And sure enough, these are two sets of data that are taken simultaneously for potassium and rubidium. This is a part of that characteristic sinusoidal structure that I showed you in the Mach Zehnder interferometer. And sure enough, we're seeing them at the same phase shift in the two interferometers. And you have to work pretty hard of these systematic effects, like making sure the effective Rabi frequency of for the rubidium and potassium are the same, because otherwise the interferometer is asymmetric, and you're not going to get any sort of nice comparison between potassium and rubidium. This data is 3-4 weeks old. This is the first time it's seen the light of day, so brand new. Let me finish up by telling you a few other things, directions we're going with this. One of the things that justified having the potassium and rubidium on this Cal device was doing exactly the interferometry and doing, for example, tests of Einstein's Equivalence Principle. But it turns out that there's a lot of interesting physics that goes on in mixtures. There have been proposals to make molecules up there. Not quite yet. But one of the things that this picture represents is what happens when you take a Bose condensate of two different atomic species, or in fact two different spin states of the same species. One of the things that determines the spatial shape of the condensate is the trap it was formed and a lot of things of this sort. But in detail, also the atom-atom interactions. One of the beautiful things about simple atomic Bose condensates is the temperatures are so low that S-wave scattering channel is the dominant channel, and a large amount of the properties of the atom-atom interactions are governed by those scattering lengths. Different species have different scattering lengths, and this means that the shapes and the interactions between the two condensates cause them, in many cases, to phase separate. This was discovered early on in the history of Bose condensation physics, so this is 97, remembering that at Gila, the first results were around 95. They produced a Bose condensate in two different spin states, and that different scattering lengths produce, by a sort of energy argument, one condensate component in the core and a different condensate component around the outside. The interaction energies between these two are repulsive enough that one species gets pushed out of the core by the other. Now, that was sort of seen by Cornell and Wyman. Unfortunately, when they tried to push that to understand how this phase separation between the two species was taking place, what happened was gravity kicked in. The two different components felt different forces, felt slightly different traps, different forces of gravity. And instead of looking at a symmetry breaking phase transition in the quantum gas, you end up seeing the effects of gravity in the trap. What does that bring to mind? Well, what if there's no gravity? So you can model this. That's how that picture was formed. I was actually involved in doing some theory work on this back in the 90s, when some of you here might have been a bit young. And what we'd like to do is we'd like to reproduce those experiments and look at the nature of this phase separation on orbit. The other thing you might have heard about are atom lasers. So an atom laser is easy to explain. I've got atoms in a magnetic trap, for example. I can use RF to flip the spins in a position-dependent way and cause atoms not to evaporate out, but to leak, say, out of the bottom of the trap. And when they do that, you get effectively a beam of atoms that's very much like a laser. There's an output coupler in the laser cavity. The output coupler for the atoms is the spin flip process. If you do that for a cloud of atoms in space, you can't just hit the bottom of the trap because there's no trap. But you can cause it to happen on a symmetric shell. So we've been doing some modeling, and we're going to demonstrate a space atom laser. What's it good for? Well, people said all kinds of great things about doing with an atom laser, but this is really just to see how well we can understand the dynamics when we do this of shells of atoms. So a shell structure is quasi-two-dimensional, and I'll mention that in just a minute for another reason. So things like some of the superfluid properties, vortices, things like this, are very different in a two-dimensional spherical geometry from, say, a three-dimensional geometry or a slab. Quick tour of some of the other things going on in the space station. This is an experiment that was proposed by Nathan Lundblad at Bates. And it's basically to create potentials for the atoms that are spherical shells by using radio frequency dressing of the atomic states. And in doing so, you can create what will be a quasi-two-dimensional Bose condensate. Each of the different teams tends to have somebody at JPL who's our point person to coordinate what gets programmed for a device like this. And you can imagine that the last thing in the world they're going to let me do is go there and program what this device Cal is going to be doing in the space station. There are all kinds of safety checks of everything that's sent up there by commands. So it's the people at JPL that you work with that truly are allowed to do all the things, unless you're on tour and they let you push one button. Early experimental results, and Nathan has just published a Nature paper on this, have started to show these smiling structures. What you should be starting to visualize here is this is a Bose condensate that's in a bowl shape. And the nodes that you're seeing here are simply that if you imagine taking a bowl and doing an absorption image of it, you'll see the concentration of the ring around the bowl giving those two lobes. And you can't do this in a terrestrial environment because gravity will basically cause all of the atoms to sink to the bottom of the sphere. It's a natural thing to ask whether the phase separation that happens in the multi-species can also give you a shell geometry, as I mentioned, and that's a place that we're pushing our experiments as well. Jason Williams, who's our point person at the operating system at JPL, has also been interested in so-called halo molecules. These are extremely weakly bound molecules, and he's got some experiments that are in queue for that. Unfortunately, they've been deprioritized because he's also the staff scientist, and obviously he would choose his own experiments to get priority. But he'll be moving into a different role and we'll start pursuing the halo molecules. Also familiar to some people in this room, certainly to me, Eric Cornell is one of there are 5 of us who were funded to do experiments to use this device. What Eric's proposal, along with Peter Engel's, was to work on FMOF states now to look at the scaling of FMOF physics over in larger and larger scales than you can do in a terrestrial experiment. They haven't actually been able to get started because it was only within the last 5 or 6 months that the potassium system began to work successfully. Is there a future to all of this? Well, there's planning. And one of the things that you learn working with an agency like NASA is you never know what's going to happen. Look, the story I told you at the beginning, George W. Bush decided the money was being wasted and just canceled the whole program overnight. But meanwhile, sometimes plans, if you don't have them, then nothing happens. There's a new entire system being developed. It's called BCAL. It's going to be built by the Germans and then flown by NASA, and we'll see how that goes. But where's this all happening? So the drop tower stuff sort of started around 2007 or 10. If that thing is some of the earliest experiments that were done with atomic clocks. They take an Airbus, they fly it up to the point where it stalls, they turn it around and pitch it back downwards. So for that period of time, it's effectively in free-falling gravity. It has many people tend to get ill when they go in this, so it's got a nickname that's the vomit comet. Moving up towards space, and then hopefully this, right around in here, the next generation of the CAL device will be aboard the space station. Russians have pulled out. I don't know what that's going to affect anything. And frankly, the truth is the space station was supposed to be decommissioned right around here, but they keep deciding they've spent so much money on it that maybe they could just keep running it for a few years longer. We'll find out. That's the end of my story. Thank you for your attention, and I'd love to hear questions.